Example 7 on page 143. A scientist working in agricultural research believes that there is a linear relationship between the amount of a certain food supplement given to hens and the hardness of the shell of the eggs they lay. As an experiment, controlled quantities of the supplements were added to the hens' normal diet for a period of 2 weeks, and the hardness of the shell of the eggs laid at the end of this period was then measured on a scale from 1 to 10 with the following results. The table shows the amount of food supplement added in the top row and the hardness of the eggshell in the bottom row. Just to try to interpret, when 2 grams of the supplement was added per day, the hardness of the eggshell was 3.2. When 8 grams were added per day, the hardness of the shell was 6.4. When 14 grams were added per day, then 9.8 was the hardness of the egg. Straight to the question. Part A, find the equation of the regression line of f on h. Find the equation of the regression line of f on h. Part B, interpret what the values of A and B tell you. And Part C, explain why you should not try to calculate the shell hardness for a food supplement of 20 grams per day. And at this juncture, then you are told that we may use sigma f to be equals to 56, sigma h to be equals to 45.8, and the mean of f bar is 8, h bar, the mean of h, we use it as 6.543. At the same time, sigma f squared is going to be 560, and sigma fh to be 422.6. We have been given those constants or values to use. Straight to part A, find the equation of regression line of f on h. Of course, we know very well that SFH, we need it because we need to get the value of A, we need to get the value of B, because we need to interpret them and substitute them in the equation of regression. SFH is going to be, as we know, sigma FH, which is going to be sigma FH minus sigma F, sigma H, all over 1, 2, 3, 4, 5, 6, 7. All over 7, and this one is going to be interpreted as 422.6 sigma FH minus sigma F, which is 56, multiplied by sigma H, which is 45.8 over 7, and this one is going to give us 56.2. We also need SFF. We also need SFF because we know very well we also need SFF. So SFF is given by sigma F squared minus sigma F squared over, of course, 7. N is 7 in this case. So at this point, we just pick the values that we need. Sigma F squared is supposed to be 560 minus sigma f, which is 56 squared over 7, and this one gives us directly 112. You can confirm those figures. And of course, we know very well, generally, if we know that B is equals to, generally, SXH over SXX. So even in this case, our B, we have only changed from XH to FH. So, and of course you can see our X is, F stands in the place of X, and H stands in the place of Y. And at this particular point, SY, so in this case, we are going to have B, in this case of ours, is going to be SFH over SFF. Having said that, then our B is now very simple. SFH, which is 56.2, which is 56.2, all over SFF, which is 112, and our B becomes 0.5018. You can confirm that. Of course, we know, having found our B, then we need to find our A. Our A, incidentally, is generally given by the mean of Y minus B, the mean of X. We just substitute this and say our Y is H, so our A in this case is the mean of H, minus B, the mean of F. Just substitute this and have our mean of H is 6.543, minus our value of B is this, 0.5018, multiplied by the mean of X, which is somewhere, which is the mean of F, which is 8. The mean of F, which is 8. And at the end of the day, you will find out that our value of A is going to be 2.5286. That is now the hardness, of course, the hardness unit. Now, find the equation of regression of F on H. And what happens is now picking all this information, because F is the independent variable and H is the dependent variable. So generally, H depends on the value of X. So the equation of regression is going to be, generally supposed to be Y is equals to A plus BX. But in this case, instead of Y, we have H is equals to our A, 2.5286 plus B, which is 0.5018x. And that is the equation of regression of our equation. Of course, if you look at part B is asking us a very simple question. Interpret what the values of A and B means. The value of A being this one, this is the value of A, this is being the value of A, and this being the value of B. Of course, A tells you the shell strength when no supplement is given. The strength of the shell, or the hardness of the shell, when we have 0 supplement added. It is actually going to capture the y-intercept. What about B? B now, B is the rate of increase of hardness of the shell for every gram of the supplement added. The rate of increase of the shell for every gram of the supplement added. If you may want to capture that, B tells you the rate at which the hardness increases with increased food supplement. And in this case, for every extra gram of food supplement per day, the hardness increases by 0.5018. Part C of the question, explain why you should not try to calculate the shell hardness for a food supplement of 20 grams. Explain why you should not try to calculate the shell hardness for a food supplement of 20 grams. Simple. If you look at our original data, the highest amount of the food supplement added was 14 grams. So you realize that 20 grams is far beyond the 14. It is not within our range. And the reason why we should not use 20 moving forward or 14 moving forward, and I'm assuming 20, we have 14, we have 16, we have 18 there, we may have 20 there. It's so far from what is already provided to us. So the value of hardness we are going to realize after using 20 grams as the amount added of the supplement is of course going to be outside the range. So it is going to be so much extrapolated, and we cannot rely on such a figure. So the value of 20 grams for F is well outside the range of F, and a value for H based on this could be very, very unreliable. It is an extrapolated value, and that is why we should not use 20 grams as the supplement added per day. All right?